Okay, making a new response video to DraftScience. Trying a new format here, so I have clipped some parts of your video here and we'll play them one by one and try to respond to them. So let's start with the first one.
Note that when we are talking about spring compression, we can talk about either the length of the compression, meaning how many inches or centimeters we are making the spring shorter, or we can talk about the duration of the compression.
I don't see any point in talking about the duration. It doesn't mean anything.
But I think that you have often said that it's duration that is important and not the distance. So for example, your definition of work is force times the duration. Am I right? So here we have two springs applying equal amounts of force, but the duration is different. So how does that play out?
Because depending on what mass I put in front of it, of course, the velocities are going to be different. The duration is going to be dictated by the velocity.
And how about the paint sprayer analogy? Does it apply here?
So what? That'll be compensated for by the math. The mass is the simple argument. Heavy things go slow, little light things go fast, okay, and it really won't have anything to do with how much pressure they can exert, in the sense that their pressure will be just a simple calculation of their mass times their velocity. Those are the only things that are relevant, and you don't need to put a 1/2 and a square on them. Those superfluous, non-real things don't enhance understanding at all. The real things are mass and velocity. The completely artificial, useless, mushy, cruddy stuff is just this 1/2, whatever that is, and a square, for whatever reason.
You've been studying these things for many years now, and many people have tried to explain to you where those come from. They have given different explanations from different points of view. So, of course, you don't have to accept those explanations as useful descriptions of reality, but still it's a bit strange that you're saying for whatever reason, as if you didn't have a clue where they come from. I think that at this point you should have some kind of idea about the reasoning in conventional physics, if you're trying to argue against conventional physics.
Which has nothing to do with reality again, and is only defended because you people say something as silly as 9.8 meters per second per 1 second squared. Per second per second. There's no per second per second.
And you say silly things like meters per second when you're talking about velocity. How does that make any sense physically? You have a distance, then you're going to divide it, but not into segments of smaller distances, but you're going to divide the distance by some amount of time. Isn't that just crazy talk? I mean, it doesn't make any sense. Until we understand what is meant by the notation in this context. So we understand that meters per second or distance divided by time is the distance traveled within that time. So it's a description of velocity. And when we understand this, it makes sense and we can use it in calculations because it works mathematically. For example, if we travel 10 meters, we spend 2 seconds doing that. The notation tells us that the average velocity is the distance 10 meters divided by the time 2 seconds. We get 5 meters per second. Makes sense and it works. And it's the same thing with acceleration. So if you accept meters per second, you just need to replace the distance by velocity, because that's what is changing over time when we are talking about acceleration. And this of course equals to meters per second squared. And let's take a look at an example. So let's say we change our velocity by 10 meters per second. So we, for example, start at 0 velocity, then we accelerate for some time until we reach the velocity of 10 meters per second. And let's say it takes 2 seconds to do that. Now the notation tells us that we get the average acceleration by dividing the velocity, 10 meters per second, by the duration, by 2 seconds. So we get 5 meters per second, which is 5 meters per second squared. So if we have this acceleration, we accelerate for 2 seconds, it's quite easy to calculate what is the change in our velocity. Well, let's actually do that. So we have an acceleration of 5 meters per second squared. We accelerate for 2 seconds. So our change in velocity is now 10 meters per second. It's really this simple. I mean, there's no tricks involved here. And I would say that this is by far the simplest thing that people have been trying to explain to you. And I just keep wondering that if you don't understand this, then is there any point in talking about the complicated stuff, the very difficult stuff, if this is way too complicated for you? I don't know, but let's go to the next clip.
Directions. And just for the sake of the argument, let's make 2 assumptions. The first is that both springs create equal amounts of total momentum, and the second one is that each spring creates equal momentums to both directions.
Okay, wrong. So that doesn't happen.
So what do you think about Newton's third law? I think it quite clearly says that the momentum would be the same to each direction, to both directions. So do you think Newton's third law was a mistake, or do you have a different interpretation of it, or what?
I mean, clearly it doesn't happen. So, as soon as this side yields, right, the light object on this spring means this light object is yielding. This 10 can't possibly go the same speed as it's going to go here, because it's getting all the energy here, because this is not going to yield at all.
Well, it's going to yield a little bit. I mean, that's just momentum. It has a higher mass, so it gains less velocity, so it's moving very slowly. And the difference why the 10 mass balls won't gain the same velocity is because the total momentum is different between the 2 springs.
So yeah, the more a surface yields, the less the thing can bounce. The more I throw a tennis ball at a wall, if the wall starts moving, the tennis ball is not coming back at the same speed. And if it moves really, really easily.
Okay, I don't think there was anything interesting at this clip anymore. But yeah, what do you think about Newton's third law? What's your interpretation of it? And oh yeah, in some other video, this is the title from a few weeks ago, you said something like this.
Velocity. All right, and so we did a simple experiment. You put ones and ones on here, and nobody would doubt, in a sense, that this experiment's been done so many times that you get the same velocity this way that you get this way. And if you put a double mass here, you'll get 1/2 the velocity going this way. So there is the sense that momentum is certainly conserved in these environments. Substantial evidence that it is perfectly conserved.
Perfectly conserved. So which one is it? Here's one last clip.
This one, they merge and they continue, and then you'll see.
Right, so this is just 5-ton train into, moving 10 miles an hour into 5-ton train moving 0. It becomes a 10-ton train. The momentum is completely conserved, and yet we lose half the kinetic energy, but we have all the momentum still.
Yes, momentum and kinetic energy are not the same thing. So Here we have the scenario you described, so 5 mass 10 velocity object hitting 5 mass 0 velocity object so that they stick together. So we end up with 10 mass 5 velocity object. Momentum was conserved, but we lost half of the kinetic energy. So what happened? In the comment section of my previous video, there was a suggestion to consider this scenario in reverse. And I thought that was a pretty good idea. So let's start with 10 mass 5 velocity object. Then something happens here so that these objects get separated. So we end up with one 5 mass 0 velocity object and 5 mass 10 velocity object. So again, momentum was conserved, but now we have twice the kinetic energy here. So what happened here? How did these two objects get separated? Because obviously they don't get separated spontaneously. Something needs to be done. You have to do something. You have to do some work to get them separated. Basically, these two objects, they need to push against each other to achieve this. For example, you can put a compressed spring in between these objects here, let it decompress. It pushes against both of these objects. It stops this object and gives this object twice the velocity. So this is the way you separate these two objects. You have to put some energy into the system. So what it means in terms of this initial scenario is that you will lose some energy when you force these objects to stick together. The energy is lost as heat energy and deformation of these objects. So that's the explanation. And this brings us to a quite interesting thought experiment. I know you love my thought experiment, so here's another one. Just one, I promise. So here we have an object with some mass, some velocity. It hits some sticky wall, so it doesn't bounce off, but it sticks to the wall. Now we know that when the object was moving, it had some movement-related energy. Let's not call it momentum or kinetic energy because those already have definitions, but let's call it something like movement energy. And how should we define this movement energy? The energy that an object has because it's moving. Well, if we take a look at the momentum, definitions of momentum and kinetic energy, what they have in common is the mass. So it's probably mass times something, but what? Something about velocity, but we can't really agree about the function, what we are going to multiply. So let's just say it's some unknown function of velocity. It could be just the velocity itself, so then it would be the same as momentum, or it could be velocity squared, or 1/2 velocity squared, so then it would be the same as kinetic energy. But we don't need to know that. It's just some unknown function of velocity the object had as energy when it was moving. But now it got stuck to the wall, so somehow the energy was lost. So the energy was conserved, but it went somewhere. So it was lost as deformation of the object or as heat energy. And for simplicity, let's just say heat. So some energy, well, all the movement energy was now lost as heat. So the amount of heat energy is the mass times the function of velocity. Okay, so far so good. But now let's consider a different scenario. So now we have two objects with the same mass and same velocity as the previous object. And now they are approaching each other, so they collide and again stick together. So how much movement energy we lost now? Isn't it twice as much as in the previous example? Because now we had two objects both having the same mass and velocity, and all that was lost. So I think it's 2 times the mass times the function of velocity. Okay, then let's consider one more scenario, almost the same, but just a moment. Yeah, but now we give one object twice the velocity and the other object we give 0 velocity. So this moving object hits the stationary object. Again, they stick together. And now, before going any further, isn't this impact the same as this one, at least in terms of heat energy lost? Because the velocity difference is the same. The difference is 2 velocities. Here's the velocities is in opposite directions, so that's why the difference is 2 velocities. So I think the amount of heat energy, the amount of movement energy we are losing as heat is the same. So it's twice the mass times the function of velocity. Now we also know that this object here, these two objects stuck together, they keep moving because of the asymmetric momentums. So they keep moving with 2 mass and 1 velocity. The momentum is of course conserved. And now, based on the conservation of energy, we can write down an equation. This is a simple equation. So what we started with, it was the one mass object moving with twice the velocity. So its movement energy is the mass times the function of the velocity, but now twice the velocity. The function of twice the velocity. And where did it go? This is the other side of the equation. Well, some of that energy we lost as heat energy. So that's the twice the mass times function of the velocity, just 1 velocity now. And this object, these 2 objects stuck together, they kept moving. So they some of the movement energy was remained in these 2 objects, or this one object, one 2 mass object. So it has the movement energy of 2 mass times the function of velocity. So this is our equation based on the conservation of energy. Now we can divide both sides with the mass. So what we end up with is the function of twice the velocity equals to 4 times the function of just 1 velocity. And what this means is that if we double the velocity, we get 4 times the movement energy. And I think we can call that kinetic energy at this point. Okay, that was it. Bye bye.